The first derivation is the useful result that is used for solving practical problems. It's the steady state 1D heat conduction through a plane wall without internal heat generation. We are going to use all the clues and we are going to solve this one useful problem. First, I will sketch the situation. Say you have a very large plane wall. This is the large plane wall that you are going to study. What is happening to the plane wall? There is a steady 1D heat conduction. Steady means the temperature does not vary in time. So temperature does not change with time. Whenever you have steady, the word steady tells you that there is no time variation. Now one dimensional tells you that the temperature only changes in the x direction. Temperature will not change in the y direction, temperature will not change in the z direction. What is the x direction? I am going to assume this will be the x direction. Okay? And the length of this wall is going to be L. It is the width of this wall. And then the area of this wall. What is the area? You can see this in the side. Okay? You can only see the area in the side. This area perpendicular to the x direction. This area I am going to call it as A. Is that clear? It is not this area, please remember. The side area perpendicular to the heat conduction. That area is going to be A. So A is the area perpendicular to the heat conduction, that is in the x direction, perpendicular to the x direction. Okay. Now, there is a steady heat conducted through this plane wall. What is driving the heat is the temperature difference. Say this wall is maintained at a temperature of T1 and this wall is maintained at a temperature of T2. And I am going to assume T1 is greater than T2. The temperature of this wall is high compared to the temperature of that wall. So what will be the direction of heat transfer? Heat will get transferred in this direction. So that will be the direction of heat transfer. Is this clear? So we are going to find an expression for the heat transfer to the wall and we are going to study how the temperature is going to vary. Here the temperature is T1, there the temperature is T2. What about the temperatures within the wall? We are going to derive expression for that temperature. What is the starting point? We are going to start always with the basic differential equation of heat conduction. So let's start with the basic differential equation of heat conduction. I am going to assume that thermal conductivity is a constant. The material of the wall has a constant thermal conductivity. So which form of heat conduction equation will we use? Rho square T by rho x square plus rho square T by rho y square plus rho square T by rho z square plus q dot by A equal to 1 by alpha rho T by rho T. This equation you have to memorize, you have to have it in memory. Now, we are going to make assumptions. What is the first assumption? Steady state. Because it's a steady state heat transfer, temperature dependence on time is 0. Temperature does not change in time. So the change of temperature with respect to time is going to be 0. So this is 0 because I am going to assume steady state without internal heat generation. Where is the heat generation term here? Q dot. So there is no heat generation. So this is also going to be 0. No internal heat generation. Right? So by assumption of that, this term is also going to go. What is the other assumption? 1D. Temperature only changes in the x direction. Temperature does not change in y and z direction. So these two derivatives are going to be 0 on the assumption of 1D. So only one term survives. This is the simplest case that the equation can be applied. So you have rho square T by rho x square equal to 0. Now we know temperature is only a function of x. Temperature is not going to depend on time. It's not going to depend on y or z. So I can use ordinary derivative instead of partial derivatives. So I can write d square T by dx square equal to 0. You get a very simple ordinary differential equation. Now you integrate this equation and you obtain the solution. Now you integrate once you get d square t by dt square. One derivative will go if you integrate once. You get dt by dx equal to constant. Let me call that constant as c1. Now you integrate once more. Another derivative is going to go. So you integrate once more.
T by x.
Integrate once more. You get dt by dx will become t. Will be the constant when you integrate, you have c times x. Now this constant of integration is going to be c2. When you integrate a constant, you have constant times x. And now the constant of integration for the second one is c2. So you get temperature is equal to c1x plus c2, which is a linear function, correct? It's the equation of a straight line, y equal to mx plus c. So it's an equation like that. So the temperature distribution is a straight line. Now how to find c1 and c2? You find c1 and c2 using the boundary conditions. What are the boundary conditions? The temperature of the left end is T1, temperature of the right end is T2. So C1 and C2 are arbitrary constant, they are the constants of integration, but they can be found using the boundary condition. What are the boundary conditions on the wall? The left boundary is at temperature T1, the right boundary is at temperature T2. So let me write the boundary conditions. The first boundary condition, see this point is x equal to 0. I told you the x-axis starts here. So this is x equal to 0. What is this? X equal to L. Correct? X equal to L. So t at x equal to 0 is equal to t1. When x is equal to 0, t is equal to t1. T at x equal to L is equal to t2. That is when x equal to L, t equal to t2. You can write it that way. We symbolically write it this way, but what is the meaning? The meaning is when x is equal to 0, t equal to t1. What is the meaning of this? When x is equal to L, t is equal to t2. Now we are going to substitute the boundary condition in this particular equation. Let me call this equation as 1. Let me call this boundary condition as 2. And this boundary condition as 3. Now we substitute 2 in equation 1. How do you substitute 2 in equation 1? You put x equal to 0 and you put t equal to t1. Right? Put x equal to 0 and t equal to t1. Now x is equal to 0 or t equal to t1. So t instead of t you put a t1.
Equal to c1 into x is 0. It is going to be
0 plus c2 is c2. So you directly get c2 is equal to t1. Now we will substitute 3 in equation 1. What is the meaning of 3? When x is equal to L, t should be equal to t2. Or you put x equal to L and t equal to t2. T should be now t2 equal to c1L plus c2. What is c2? T1. Now you rearrange for c1. You take t1 to the other side, you have t2 minus t1 divided by L. So c1 is t2 minus t1 divided by L. Clear? It's just a rearrangement. Now we will erase this. Now we get the temperature distribution without any arbitrary constants. I substitute C1 and C2 in this equation 1. So equation 1 becomes T equals, can you tell what happens? T2 minus T1 by L.
Okay.
Plus into X plus
C2.
What is C2?
T1.
I'm going to just substitute C1 and C2 into this expression. So T1, T is equal to T2 minus T1 by L into X plus T1. Correct? Now I'm going to rearrange this a little bit and write it as T1 minus T2 by L into X. This is the temperature distribution in a plane wall. Is this clear?
Okay.
So this rearrangement is done because T1 is higher and T2 is lower. I want this term to be positive. And always the temperature is going to be less than T1. T1 is the largest temperature. For any X, the temperature is going to be less than T1. So it makes sense if you write it this way. This will be available in the data book. You can find this expression probably in the data book. I write the number and the page number and the equation number Now we found the temperature distribution. So this gives you the temperature distribution in the plane wall. Right? It's a very important quantity. What do you learn about the temperature distribution? How does the temperature look like? If the temperature here is T1 and here the temperature is T2, then every point between any x, this is x, right? If you take any x or any plane at a distance of x unit from the left hand, the temperature here is T. This temperature is given by T1 minus T2 by L into x. Here L is the fixed quantity, L is the width of the wall, x is varying. Depending on x, you get the temperature anywhere. And if you plot the temperature, it's going to look like a straight line. Because the equation of this is y equal to mx plus c. It's a straight line equation. The temperature distribution is a linear temperature distribution. We call it as a linear temperature distribution. Okay. Now the second quantity of interest is the heat transfer rate. If you know how the temperature changes, second very important quantity is if this is at T1 and that is at T2 in a steady state, how much heat is going to be transferred? Continuously heat will be transferred. So now we will derive the expression for the heat transfer rate. Whenever you are finding the heat transfer rate, the equation that you use is the Fourier's law. In conduction, wherever you find heat transfer rate, you are going to use the Fourier law. What is the formula for Fourier's law? Qx equal to minus Ka into dt by dx. So 1D heat conduction, so I use 1D derivatives. Now you know T. We will differentiate and find dt by dx. Can you differentiate this equation? We will differentiate first this equation. If you differentiate T, what do you get? dt by dx is equal to T1 is a constant. It's the left temperature. Derivative of a constant is 0. Minus 0 minus. That's a constant. Constant into x. Keep the constant out of differentiation. Derivative of x is 1. So that constant you will directly get T1 minus T2. Is that clear? So this will be dt by dx. I repeat, if you differentiate this equation, you will get dt by dx. Derivative of t is dt by dx. Derivative of T1 is 0, it's a constant, doesn't contain x. Derivative of the second term is some constant times x. You will get the constant out of differentiation. Derivative of x is 1. So this will be dt by dx. Now we will substitute that here. Minus Ka into minus T1 minus T2 by L. Is this clear? Now this minus and that minus in the Fourier law will cancel. In dt by dx there is a minus. In Fourier law there is another minus. They will cancel away. And you get Ka T1 minus T2 divided by L. That is the formula for heat transfer to a plane wall. If there is a plane wall, then this will be the amount of heat transferred to the plane wall.
Okay.
Okay. This equation, the expression for temperature distribution, can be found in page number 43. All the results relating to a plane wall can be found from page number 43 in your textbook.